So as you know, Joule has a high impact and high impact factor over 40 since launch in the past 5 years. It's rising quite quick. And Joule provides a home for outstanding and insightful research, analysis, ideas which addressing a global challenge, the need for more sustainable energy. So Joule is a distinctive and a forward-looking journal. We bridge the disciplines and skills of energy research. So Joule connects all who are researching and analyzing the challenges, scientific, technical, economic, policy, and social, to provide sustainable energy solutions. So Joule spans skills of energy research, from fundamental laboratory research to energy conversion and storage, up to impactful analysis at the global level. So Joule in particularly looks to serve a real energy world applications. So green energy transition is our current prioritized theme. So we are joining One Earth to work on the nexus of energy and environment. As we know, the decarbonization includes a mix of technologies spanning from the direct removal of carbon dioxide from the atmosphere to its capture from industry, utility scale, exhaust streams, followed by utilization or reliable storage of CO2 on a time scale and magnitude that will have a positive impact on our current climate change crisis. So according to a recent analysis Angela showed to us, the industry contributes 40% of the total emission, which is a heavy portion on the total emission. So it is thus urgent for us to discuss how to decarbonize the industry. And it's of high urgency to develop both mitigation and adaptation strategies to minimize negative climate impacts associated with heavy industry dependence on the fossil fuels. So today, we will bring you the key messages and a brainstorming on what different communities can contribute to decarbonize the heavy industry. So we hope to come up with valuable insights to the heavy industry community and stakeholders to understand their decarbonization options and the potential impact of their decisions in terms of carbon emission reduction. So here we are very honored to have Angela and Professor Sabbie Miller, Dr. Sergey Paltsev, and Mr. Zhiyuan Fan to join this board. And Professor Amory Lovins contributed a very nicely recorded talk, which I will play after Angela's talk. So the board all together, they will share their views in the next 2 hours, and the audience get a chance to ask questions too in the next 1.5 hours. My colleague, Dr. Shanshan Zhang, the editor of One Earth, is collecting the questions from other streams. So thanks, Shanshan, for the great support here. Last not least, I know it's not very late for Angela, for Sergey, for Zhiyuan, and it's late afternoon for Sabbie. So I would like to invite everybody to express our sincere appreciation to your flexibility to make this discussion possible. So thank you very much, and let's crack it. So first, please join me to welcome Ms. Angela Anderson. Angela is the Director of the Industry Innovation and Carbon Removal in the Climate Program. She leads the World Resource Institute's growing portfolios of working in industry decarbonization and carbon removal, and aims to change narratives around how to abate sectors and promote the natural and technological interventions required to achieve net zero targets. So in the next 30 minutes, Angela is going to walk us through the pathways to decarbonization heavy industry. So let's welcome Angela. Angela, your time. Thank you.
Thank you. It was great to chat a little bit with my panelists before you got on. And I will just tell you, I had every intention to send you all the PowerPoint before we got started. And I was tweaking it until 5 minutes ago, as you imagine. But I will tell you that it is a broad overview of the tools at our disposal to decarbonize heavy industry. And I am looking to you all to kind of dive a little deeper on specific sectors. And it sounds like that's kind of how we're organized. So I will not be talking a whole lot about clinker substitutions or but I'm happy to move on, Rose, if there's. I did want to get a chance to experiment to make sure. I have not done a presentation on Zoom before, so I did want to make sure I could load up the presentation, and if you could walk me through that, I would appreciate that.
There is a green button which you see down there. It's called share screen.
Share screen, there we go. All right.
And then you should see your presentation or one of the screens.
Okay, and then share, okay. And then from beginning.
Wait.
We are waiting there. It's loading.
Oh, okay.
Okay, perfect.
All right. That's how
Now,
it works. Okay.
Perfect.
Thank you. But I'll take that down because you are going to start with a introduction slide, right?
No, I think we are waiting for you. So you should go ahead and move on. That's my understanding, right, Rose?
Yeah. I think we're frozen again.
Yeah. No, I think you can go ahead and just present, and then they will follow.
I didn't think we were starting until straight up 9. And she talked about starting with an introduction slide, but maybe I'm wrong.
And it looks like we lost our host again. So. Hello, Rose. Are you back?
Hi, I'm back. No, I think it's now for Angela to present her slides. Angela,
Okay, so we're
please.
ready. All right.
Sorry for the delay.
All right, well, good morning and to some of you, and good evening, wherever you are in the world. It's a pleasure to be here with you to discuss how we can take carbon and other greenhouse gas emissions out of the industrial sector over the next few years. Many technological solutions currently exist to make significant progress in this sector over the next decade. And emerging solutions make it possible to imagine a net zero industrial sector by mid-century. We're going to look at these solutions briefly and the work underway around the globe to help drive industries, consumers, and governments to adopt them. And we'll take a brief look at US and China as the world's largest emitters, examining how they can drive both near-term progress and the R&D necessary for ultimate decarbonization. The climate conference in Glasgow, COP26, featured announcements that really indicated that the world is turning its attention to the industrial sector. Countries and companies are coming together around roadmaps on industrial decarbonization, many of those announced in the COP. US and China both specifically endorse specific goals and benchmarks in the Glasgow Breakthrough Agenda, with China specifically engaged in hydrogen. And both countries, as a part of mission innovation, they'll be working towards some new missions to decarbonize industry, enable carbon dioxide removal, and produce renewable fuels, chemicals, and materials. Also, the US-China declaration that was announced at COP26 indicated there would be an enhanced climate action in the 2020s, including specific work in industrial areas like methane reductions, key areas related to the circular economy, such as green design, and deployment and application of technologies such as CCUS and direct air capture. All this attention is justified and perhaps overdue, as the market sector contributing around a third of global greenhouse gas emissions. It is important that the world turn its attention more deliberately to efforts to decarbonize industrial processes. This sector creates the stuff of daily life, from pharmaceuticals and plastics to cars, trains, roads, and buildings. So we have to find ways to create those foundational materials in ways that do not threaten the climate. Just 3 industries, iron and steel, chemicals and plastics, and cement, account for 55% of industrial emissions. So focusing on these limited set of products and process improvements can really generate some outsized results. To underline the fact that the time is right, on March 9th, we heard from the IEA that the world hit the highest greenhouse gas emissions to date, driven by energy and industry. The 6% increase in carbon emissions in 2021 was in line with the jump in global economic output of 5.9%. This marks the strongest coupling of carbon emissions with gross domestic product since 2010, when the world emerged from the global financial crisis. This rise in emissions indicates one thing to me. Our initial rebound from COVID-19 signals that we do not appear to be building back better yet. And it's important to remember to build back better for everyone. Our fight for a livable climate is not just about greenhouse gases. We must also pay attention to the activities that often pose health and safety risks to the communities surrounding these facilities. And we have to engage these communities in a discussion of the future of the facilities and the future of the industry. As we build a new sustainable economy, we need to do it differently. As we decarbonize the industrial sector, we need to do it in a way that engages, benefits, and limits harms for marginalized communities that have so often borne the brunt of the adverse impacts of industrialization. We're focused on heavy industry today, but it's important to put it in the context of the overall energy transition. This chart by the Energy Transitions Commission really helps envision how the massive changes in the energy industry will play out throughout the economy. While electrification is going to play a huge role in decarbonizing most of the economy, in 2050, we will still see biomass and fossil fuels playing a role, according to their analysis. Some of the zero carbon electricity and fossil fuels will be used to produce hydrogen, and this analysis suggests will be primarily used in heavy industry, alongside with fossil fuels and carbon capture. Here's another way to look at it, breaking it down by industrial sector by its largest emitters: cement, steel, and chemicals. You see the electrification potential as a power source is around 25%. With hydrogen taking up to another 1/4 to 2/3, and fossil fuels with CCS still providing up to half the energy in most sectors, except steel, where electrification and hydrogen, it appears, can drive out all but about 20% of fossil fuel use. So with that big picture in mind, let's take a look at the tools at our disposal. Choices of feedstock and energy sources, efficiency improvements, and capturing and storing carbon are the primary interventions that will deliver the greatest results. The emerging focus on clean industrial hubs can help maximize the benefits of these measures and can collectively address the adverse impacts of living near and working in these facilities. Increased circularity and reduced demand can also play a significant role. And while bringing industrial emissions to near zero is difficult, it is quite possible, given the range of mitigation options and the emerging technologies. Energy efficiency, one of the most accessible interventions available today. A factory or a facility can undertake efficiency measures that often have the added benefit of providing a nice return on investment. There are many organizations and consultancies available to advise companies and countries on energy efficiency, but I did want to draw your attention to the Industrial Energy Accelerator. This is a UNIDO-led network that works to increase the uptake of measures and technology to boost efficient energy use. Working in country allows the accelerator to forge critical relationships with local governments and industry players, and it fosters collaboration across sectors, stakeholders, and countries. The accelerator also designs solutions tailored to specific country needs, operating programs in over 10 countries, which are home to large and growing industrial sectors with huge energy efficiency potential. One of the countries that have been involved in that accelerator is China. China invested heavily in energy efficiency since the turn of the century. Its economic growth has been accompanied by those efficiency efforts, and it's led it to become, according to the IEA, the world heavyweight in energy efficiency. And while efficiency and electrification are important pieces of the decarbonization puzzle, deep decarbonization in the industrial sector is going to require fuel shifting away from fossil fuels and/or capture carbon emissions from the burning of those fossil fuels. Carbon capture and storage and utilization are likely to be key interventions in industrial decarbonization. CCS technology has been in use in the United States since the 1970s, and there are 26 large-scale facilities using it. Critics of carbon capture and storage cite that track record to cast doubt on its effectiveness and its scalability, and they may have a point. But it's also clear that the lack of a clear climate policy in the US and the lack of adequate investments to invest in the technology has hampered its adoption. One possible role for CCS and global decarbonization can be found in IEA's Sustainable Development Scenario, which defines a pathway where 15% of global emission reductions up to 2050 are delivered by CCS. If that turns out to be the case, the installed capacity of CCS would need to increase 100-fold by 2050. The capital requirements for this would be between 650 to 1.3 billion US dollars, depending on the rate at which CCS costs reduce with installed capacity. Governments are going to need this to help this process along. They may need to define the role of carbon capture in meeting their national emission reduction targets. They can support the identification and the appraisal of geological storage resources, and they can identify opportunities for CCS hubs and facilitate their establishment. These kinds of things are happening in the United States today as a result of the infrastructure law passed last fall. And in that bill, there is also significant public funds available to provide grants, low-cost finance, and/or loan guarantees to reduce the capital costs of CCS investments. In addition to efficiency and CCS, most facilities will have to look at fuel switching, and hydrogen is projected to be a likely alternative to fossil fuels in heavy industry, in part because of its ability to produce very high temperature heat. Blue hydrogen, while more readily developed, has its challenges. Widespread adoption of any form of zero emissions reforming is only prospective today. Most SMR carbon is vented into the atmosphere because selling CO2 to buyers like the oil and gas, food and beverage, and chemical industries fails to offset the cost of separating and transporting the carbon. This indicates that making clean fossil-based hydrogen is doable today, but markets and sequestration opportunities have to expand while production costs fall. Green hydrogen uses 100% carbon-free energy to power electrolyzers that split water into hydrogen and oxygen molecules. Electrolyzer costs are currently very high, and the capacity factor and availability of renewable zero carbon energy, those two factors will limit green hydrogen development. These factors should improve by 2050 as electrolyzers are mass produced and the availability of zero carbon energy increases. Hydrogen is a hot topic around the globe, and countries are moving fast to attract investment and incentivize scale up. Most decarbonization models assume the cost of green hydrogen will fall over the next few decades, and it will become the dominant source of hydrogen. But that is not a certainty by any means. For example, WRI's analysis of ways to decarbonize refineries found that blue hydrogen will likely continue meeting refinery demand until 2050. Why? It's because existing refinery and hydrogen clusters enable cost-reducing economies of scale built upon natural gas and hydrogen transport networks. It's likely that these factors exist in other countries as well. The map on the left shows some of those existing networks in the US. As the US and other countries build new industrial and hydrogen hubs aimed at fostering net zero emissions, this factor could play less of a role, but only if those hubs are properly designed and implemented. The map on the right shows the potential for green hydrogen and possible hubs connecting them to consumers, again, in the continental US. However, the renewable ramp up projected in our modeling may simply not happen as quickly as the models predict. There are tons of issues related to that ramp up, from the availability of labor, siting complications, build out of transmission, and it simply just it could not happen quite as quickly as we need it to. And that could slow the development of green hydrogen as well. Cement, concrete, they're all going to need the interventions we just talked about to decarbonize, but they also need established standards for their product to be considered low carbon or near zero carbon to qualify for public and private procurement programs. Several initiatives are underway to help develop these standards, and there's more than what I'm going to mention right now. But under the Clean Energy Ministerial, we're proud to have joined an effort that UNIDO is leading to foster industrial deep decarbonization. They've brought together a diverse coalition of governments and private sector players and civil society, think tanks, et cetera, that are working to decarbonize steel, cement, and concrete. IDI plans to develop consistent global standards for public procurement programs. And within the next 3 years, it expects to have enabled a minimum of 10 governments to pledge to reducing embodied carbon emissions in all major construction projects by 2050. It's a very ambitious undertaking, and proud to be a part of it. The First Movers Coalition is more focused on private sector pledges. This was announced at this effort, initiated by the US and supported by the World Economic Forum, is focused on private sector pledges to create markets for near zero carbon materials. One of the primary goals in its first phase is to reduce 1/3 of the world's emissions with a focus on hard to abate sectors. In that definition, they include aviation, aluminum, chemicals, concrete, shipping, steel, trucking, and direct air capture. The FMC plans to define purchasing commitments for emerging technologies needed by net zero across these sectors, secure 2030 commitments from critical players across the value chain to jumpstart action in the 2020s, and facilitate the implementation of those purchasing commitments. It's an interesting sector, it's an interesting private sector approach, and I think these two kind of demonstrate some of the activity underway to set these standards in public and private sectors. Now let's take a closer look at what the US and China are doing to support industrial decarbonization. Overall, China set a goal of reducing carbon neutrality, or of reaching carbon neutrality by 2060, and it's setting near-term sectoral peaking goals to get to that neutrality. China right now leads the world in both solar power and coal use simultaneously. Those two factors are important in analyzing the prospect for lowering industrial emissions. Just a few weeks ago in February, the government announced 18 directives for the country's industrial economy for 2022. At least half the measures are directly related to China's climate goals. They included offering subsidies for the purchase of new energy vehicles and the installation of charging stations, promoting financial instruments to support clean coal utilization and carbon emission reductions, both to meet their energy security and their climate goals. And they've developed a tiered pricing system for electricity based on energy efficiency, which some analysts suggest could lead industrial users to build their own solar plants and invest in their own renewable generation. The measures announced also included orders to incentivize solar and wind power innovation, retrofit low efficiency coal-fired power plants, and step up energy conservation and emission reductions in energy intensive industries. Our office in China, WRI China, assessed China's progress towards the 2020 NDC prior to COP26 and found that these climate targets have been met, like many others have found, putting China on track to meet the NDC targets it set in 2015. It included a scenario of more ambitious action that it also thinks is feasible. The report acknowledged that industry is currently the largest source of greenhouse gas emissions and the main source of CO2 emissions in China. They note that promoting the conversion of coal to gas or electricity and increasing R&D of hydrogen energy technology is important, but will entail high costs and technical challenges. Their analysis indicates that the combination of CCS and carbon sinks from forests can increase carbon absorption by 1.2 gigatons in the near term and reduce 17.1 gigatons over the next 30 years. This is an important factor when you consider the IPCC's indication that we're going to have to remove a significant amount of carbon, I think, by 2050. Our colleagues' report recommended ways to lower the demand for industrial products, steel, cement, plastics, and chemicals by applying greater circularity and developing alternatives for chemicals and building materials, which would ultimately reduce industrial production capacity and the emissions that come with it. In the United States, we like to consider ourselves a leader in climate change. But our challenges in really delivering on that leadership role are primarily political. The lack of regulatory certainty because of the changes in government policy as administration change has hindered investment in decarbonization. There are also challenges of siting and building clean energy and carbon management infrastructure. And there's economic challenges, which are not unique to the United States, but have sort of exacerbated those political complications as we face rising inflation, worker shortages, and deficit spending. But that's all the bad news. Under the Biden administration, the US did set a target and a goal of reaching net zero by 2050. It's a really exciting endeavor. Their low carbon standard outlines the ways that we can get there, and I would say the major measures that we're utilizing to meet that goal are a ramp up of renewable energy or clean energy, aiming to get 100% clean energy by 2035. We're also leaning in on electrification of transportation and buildings, incentivizing the use of industrial CCS and the build out of hydrogen, and public procurement programs to drive low carbon materials markets. And of course, a commitment to both nature-based and technological carbon removal. The infrastructure legislation that was passed last fall included significant investments in all of these areas, including tax incentives and government projects, pilot projects, grants, et cetera. It's the largest government investment in climate change that we've ever seen in the United States. Probably the largest investment in many problems that the government aims to tackle. It was a significant step forward, and the implementation is going to be key. WRI is our program focused on has focused on the U.S. industrial innovation, as you can probably tell. Our industrial decarbonization projects have focused on domestic policy and trying to advance bills like that infrastructure bill. And we've co-convened the Industrial Innovation Initiative. It's a series of corporations, NGOs, and state government officials that have agreed on a blueprint of industrial policies that could help decarbonize the sector by 2050. WRI's also published a series of working papers on cement and steel product standards, and we've outlined a pathway to decarbonization to decarbonize refineries. Soon we'll release a similar paper on how to decarbonize the petrochemical industry. No small feat. Before we move on to the other panelists, which I'm really enjoying and anxiously anticipate hearing from. I want to note that everything I've talked about, the solutions available today, the emerging technologies, country actions, and global agreements may make it sound as if industrial carbonization won't be too hard, but I think it will be very hard. Changing industrial operations, installing new technologies, retrofitting factories to adopt new fuel supplies, adjusting consumer expectations and adjustments along the supply chain, all amidst global competitive fears and political forces that resist change. All these things indicate to me that progress will be very slow if we continue at the pace we're going now. But the optimist in me thinks we are entering a period of very rapid change brought about in part by the pandemic and the power sector transition. And whether it's corporate commitments, global negotiations, or marching in the streets, we are hopefully accelerating action on climate in all economic sectors, in all walks of life. As important as policies and technologies are, a powerful uniting vision must drive this transition. And I think, and at least I hope, we're finally on that way towards that shared vision. Thank you for your time and attention, and I'll turn it over to our host.
Okay. Thank you very much, Angela, for the comprehensive analysis and of the current situation with the different sectors of the heavy industry. And now we look forward to dive deep into possible solutions in the next panel discussion. But before that, please let's welcome the three panelists today, and we will give them. We will invite them to give like a brief summary of their research before the discussion. So our first sharing will be given by Professor Amory Lovins, who unfortunately cannot be here, but he recorded his talk. So let's like walk through his talk. Wei Miao, please play Amory's talk now.
大家好，我叫卢安武。Thank you for the honor of letting me enlarge our system boundary by introducing concepts from integrative design, a proven way to optimize industries, buildings, and vehicles as whole systems for multiple benefits. As this free bilingual paper shows, integrative design can make energy savings several-fold bigger, yet cheaper, by not adding more or fancier devices, but using fewer and simpler devices, more artfully chosen, combined, timed, and sequenced. Integrative design is not a depletable physical resource like oil or copper, but an infinitely expandable assemblage of ideas, depleting only stupidity, a very abundant resource. Integrative design starts by cultivating original mind, beginner's mind, child mind. Shedding all assumptions and preconceptions yields astonishing results. RMI's $50+ billion worth of diverse industrial redesigns typically found 30 to 60% retrofit energy savings, paying back in a few years, and in new builds, 40 to 90+% savings with generally lower capital cost. Thus, redesigning pipes and ducts can save about 80 to 90% of friction, 97% in my house, potentially saving 1/5 of the world's electricity, or half the coal-fired electricity, and typically paying back in less than a year in industrial retrofits and instantly in new builds. Cost and emission savings are about 10-fold larger. Reversing compounding losses makes components much smaller and cheaper. Thus, low-friction pipes make the blue pump tiny, and it's raised up to meet the pipe rather than dipping the pipe down to meet a pump on the floor. Laying out pipes before equipment staggers the tan chillers from a neat row to eliminate pipe elbows. Friction and capital cost plummet. Yet such rearrangement of designers' metal furniture is in no standard engineering textbook, industry forecast, government study, or climate model because it's not a technology, but a design method, and few people yet think of design as a scaling vector. My forthcoming how-to guide, The Tao of Pipes, will bring this exciting practice back to China from my Singaporean master, Liang Lok, Li Yonglu. 4 years ago, the Energy Transitions Commission found that heavy transport and process heat could be completely decarbonized by mid-century at modest cost. Their analysis was convincing and helpful, but seemed to me conservative. So last summer, 2021, these technical and business papers showed how that decarbonization is not particularly hard, just differently hard, and now more likely profitable than costly, if we enlarge the system boundary so it encompasses everything the solution requires. Before providing less, cooler, cleaner, and renewable process heat, we should first reduce demand for those energy-intensive materials. Need less, use other, use less, use longer, use again, align incentives. Only then should we redesign production. This sequence can save at least half the world's cement and steel, rising to 3/4 by correctly specifying and installing concrete. Then it's far cheaper to improve the and easier to improve the fourfold smaller process or its heat source. Buildings half of cement and a third of steel is largely wasted by inefficient structural design. Tension structures can save about 80 to 90%. Pouring concrete beams into fabric rather than prismatic forms saves half. Concrete bridges support mainly their own weight, but 3D printing an airy dendritic structure supports mainly payload. Corrugating a thin concrete roof slab or floor slab can make it fourfold lighter. And floor slabs are half the weight of a mid or high-rise building, plus supporting structures. We can also save another roughly 15% of core structural materials, 3/4 of the energy, and much time and cost in a mid or high-rise building while increasing net rentable space by a stunning 55%. This 3-for-2 design, as in the Singapore pilot project at the upper right, eliminates a vertical meter plus of mechanical plenum at each story, so 3 stories with normal 2.8 meter ceiling height fit into the standard height of 2 stories. Cost, complexity, and time fall dramatically. Everything gets better. Twisting the Shanghai Tower made it stiffer, cutting wind loads 24%, and structural materials cost $58 million. But can't other construction become that brilliant? The world's largest unreinforced concrete dome still stands in Rome's Pantheon after nearly 2,000 years. Today, about 60% of the world's cement is made in China, where concrete buildings reportedly last an average of about 30 years. Short life and inefficient design use far too much cement. Why can't we build as well today as the Romans did in the Han Dynasty, especially with new business models? Rather than selling more tons, a basic materials provider or others can lease the services the customers want and reward the designers and builders who provide the best services with the fewest tons. In a world of elegant frugality, using fewer tons more productively, early adopters are likely to win. Combining integrated design with such business models can help raise long-run global energy productivity by about 5-fold, perhaps more. If we focus on innovation just in the important but incomplete area of technology, then game-changing designs and business models are not recognized, taught, delivered, expected, or reported. But China could lead the world in rapidly shifting these novel practices from rare to normal. You'll find a readable introduction to that approach in this design and business book. Thank you all for your good work and your kind attention.
In energy efficiency research into this short introduction. I'm sure, like me, you enjoyed this a lot by his thoughts of the fewer, the simpler, and less is more. So he also nicely covered the efficiency of cement on the concrete part, and we will have more discussions on that. So now let's move on to next panelist. We welcome Professor Sabbie Miller from UC Davis. So one of her recently research focus is on the performance and sustainability guided material design. So she derives tools and methods to design sustainable infrastructure materials. This includes the integration of sustainability into structure design and assessing their efforts of improving the durability of materials. So welcome, Debbie. Welcome, Sabbie. Sorry, the floor is yours now, Sabbie.
Thank you so much. Let me quickly bring up my slides. You will momentarily see my dog as I bring them up. I apologize for that. There we go. Okay. Hi, so I'm Sabbie Miller, and today I'm going to focus a little bit on the research that we do in my group that looks at pathways to net zero cement, as well as actually, in fact, net uptake, GHG uptake cement, so carbon mineralization within our cement-based materials. Our group does, in fact, do other work as well, including quantification of environmental impacts for other types of material classifications and some other aspects of novel materials design. But since this is all about industrial decarbonization, of course, we're going to discuss cement. All right, so with that in mind, a quick bit of motivation in terms of the mass of our materials and where our greenhouse gas emissions are coming from. We've had this huge buildup of infrastructure materials as time has elapsed. And if we look at the massive material that we've produced from 1900 through 2015 summed together, the vast majority of our materials have actually gone into building stock. If you look at those numbers relative to the amount of material gone to feed humans and livestock, as well as the amount of material gone to energy resources, you actually end up seeing that building stock is almost half of our materials consumption. So this is this really large stock of materials that we've been working with. If you look at a snapshot of 2016 greenhouse gas emissions, you'll end up seeing that the production of materials is in fact a significant fraction of our global greenhouse gas emissions, and the vast majority of those materials end up being used in infrastructure applications. So while some of our high emitting materials like steel do end up getting used in a variety of applications, what we end up seeing is that our cement sector really does predominantly support our infrastructure applications. So this particular chart here is showing you, if we look at all of the materials that we're making, how many of those are going into infrastructure, and we end up seeing that over 10 gigatons of greenhouse gas emissions are just to make our infrastructure materials, or sorry, rather to make our materials. Just over 6 gigatons are to make our infrastructure materials. When we look at this breakdown of our infrastructure materials, we see the vast majority of emissions are associated with producing our cement-based materials like concrete. Now, there's been a really large drive associated with why these emissions are occurring, and it's not because cement and concrete are bad for the environment. In fact, if you think about this in a per mass basis, a kilogram of cement is really not a very high emitting material. And if we as a society only needed 1 kilogram of cement every year, no one would discuss it in terms of decarbonizing. But rather, the issue is that we need over 4 billion tons of cement annually. And that really high level of consumption is actually what's driving the high level of emissions. And the high level of consumption is strongly tied to population demands and affluence. So this is the IPAT equation. For those of you who are familiar with it, basically impact is a function of population, affluence, and the technology available to those populations. And if we look at our population in 1900, we had about 1.5 billion people on the planet. In 2000, that had grown to be 6 billion people on the planet, and now we're at over 7.9 billion people on the planet. And with these people, we have a need to meet their societal demands, including infrastructure systems. We need roadways, we need buildings, we need systems that can get fresh water to people and wastewater away from people. And a lot of those end up requiring materials such as cement. And in fact, what we've seen over just a very short time horizon, this is about a 60-year time horizon, the world production in terms of kilograms per person, we end up seeing that our demand for infrastructure materials has really gone up. Our demand for wood has actually stayed relatively similar per person, but keep in mind, there have been more people. Our demand for steel per person has gone up, and then of course, there have been more people, and our demand for cement has also gone up and has gone up much faster than our demand for steel and wood. Now, the tricky thing here is that cement isn't the final product. Cement is a powder that is a hydraulic binder that when it reacts with water can solidify and basically forms synthetic rocks. The most common of those synthetic rocks is concrete, and concrete has about 7 times the mass of cement. So for every kilogram of cement we're consuming about 7 kilograms of concrete. Now, if you want to think about this in terms of overall consumption, when we're trying to produce a material like concrete, we use this hydraulic binder cement. We have to mix it with water to get it to solidify. And then, of course, the vast majority of what we're putting into our concrete is actually a very low impact material from the perspective of greenhouse gas emissions. It's predominantly crushed rocks or rocks that have been quarried from other types of resources, excavated from rivers, et cetera. And what we end up seeing is that this composite material is what's supporting our vast infrastructure systems around the world. And if you want to look at about where we end up using those composite materials, you see that buildings end up being one of the largest demands for our cement-based materials, but we also have a large amount going into streets and highways, with some other aspects going into things like utilities and water management. So when we try to decarbonize this particular sector, we have to look at it from the context of, well, on a per kilogram basis, it's actually not a high emitting material. It's really tied to our large demand for this material. We're going to use it in very long-lived applications, our infrastructure systems, and we need a lot of it for those infrastructure systems. So when we want to decarbonize it, there's actually these potentials across the whole value chain to start to reduce the greenhouse gas emissions associated with this material. A lot of discussion ends up occurring at the manufacturing level, and I'll show you why in just a moment. But in reality, there are also opportunities at the material design level, the structural design level, as we just heard from our last speaker, as well as at the end of life phase of the use of this particular material. So the reason why most folks focus in on manufacturing is because that's where the greenhouse gas emissions are coming from, is when we manufacture our cement. So while cement is just a component of concrete, the other constituents that we put in are such low greenhouse gas emissions that rather than focusing on the greenhouse gas emissions of concrete, we usually focus in on the cement binder. And to produce cement, we need a fair amount of limestone as well as clays, which facilitate the use of some silicates that are necessary to get the right properties out of the cement and get it to bond properly. Now, in order to make the cement, we take our limestone, we take our clay. With the limestone, we actually have to decarbonate it to turn it into something that's closer to lime. That decarbonization of our limestone releases carbon dioxide. So if you imagine calcium carbonate turning into lime, there's CO2 that's got to go somewhere. And there's a little bit of energy necessary for that process to occur. When we want to make clinker, which is a solid precursor to our cement, we have to incorporate the silicates. We use amorphous silicates with this lime base in order to form calcium silicates, which then are allowing us to make this hydrate product at a later stage. And in order to get the calcium silicates to form, we actually need to cook the material at an even higher temperature. While this particular chart calls it out at 1500 degrees Celsius, our more recent kilns, this is a slightly old diagram, are closer to the 1400, 1450 degrees Celsius range in terms of the temperature that's necessary. So in order to form these calcium silicates, very high temperature, and as a result of that high temperature demand, we have to use energy resources. Commonly, we don't use the cleanest energy resources for this particular stage. And so we also have emissions from the energy resources. We have carbon dioxide coming from limestone decarbonation, and we have carbon dioxide as well as other greenhouse gases coming from this energy demand, just to manufacture this one material. So what we end up seeing is manufacturing is oftentimes focused on in terms of how do we decarbonize this material. However, we also need to take into account that this is a material that has to perform for a very long time. We want our roadways to work. We want our buildings to work. We want our wastewater systems to work. So material performance has to be addressed, and any type of manufacturing shift that could potentially lose some of the material performance has to be taken into account such that we can design appropriately for it. Now, with that in mind, there are mitigation strategies throughout the life cycle, which I am happy to discuss in more detail in the panel, but just to give you some sense of what we've been looking at in our group, we do look at manufacturing improvements such as alternative energy resources, alternative raw materials. Of course, the alternative raw materials can then change some of our performance characteristics. We have looked at the materials design level. This includes things like how can we optimize the concrete mixtures that we're using such that we don't need quite as much cement? Are there alternative mineral resources that we could use at the mixture level when we're producing our concrete that again start to lower the amount of cement that we actually need? We've also looked at things like how do we start to design better based on selecting an appropriate strength, selecting an appropriate reinforcement ratio. And actually, before I move on too much further from that, when I say lowering the cement content, I really mean lowering the clinker content, that solid precursor that has those high levels of greenhouse gas emissions associated with them. Some cements already have very low clinker content. So there's many potential areas that we could start to improve as we start to look at our design by, again, selecting the appropriate components as we're engineering. Elongating the use of our materials, as was mentioned by our previous speaker, can again potentially offset our demand for new materials. And at end of life, we could actually benefit from the fact that concrete can carbonate. Basically, what ends up happening is that our concrete, the cement that has already hydrated within this material, can interact with atmospheric carbon dioxide if there's enough moisture present, if there's enough exposure to the carbon dioxide, basically under the right environmental conditions. Now, while we're using our concrete, not a heck of a lot of this carbonation occurs because in reality, a lot of our concrete is in this bulk area and very little is the external surface that can get exposed to atmospheric carbon dioxide and facilitate this carbon mineralization process. However, at the end of life, we can knock down our buildings, crush them, get a really high surface area to volume ratio, and potentially facilitate a faster carbonation process occurring. Now, this is an area that folks are still poking around with, trying to see how we could best use this particular mechanism, but this could start to lead to a bit of a sink of atmospheric carbon dioxide from a material that was already emitting carbon dioxide to begin with. Now, in addition to that, we have this added complexity of, well, we've got these infrastructure materials. We need them for our infrastructure systems. Basically, our systems and services are highly dependent on the materials that are used. But to produce those materials, we have resource consumption, we have energy consumption, and oh, by the way, our structures and services also require energy. And by the way, our energy systems require structures and services. Added to that complexity, we have the greenhouse gas emissions that we're discussing in heavy part today, but also we have air pollutant emissions associated with our infrastructure material production. We have waste flows associated with our materials production. And in fact, we also have a fair amount of water demand associated with the production and several types of flows associated with producing cement as well as other infrastructure materials can actually lead to health burdens. And so what we end up seeing is a pretty complex mix of things that we're looking at when we're trying to analyze these types of materials. And when we decarbonize our materials or aim to decarbonize our materials, we need to be very careful to not cause things like resource scarcities, localized scarcities of the minerals that we need or other components such as water that we would need, and we don't want to cause localized burdens such as human health impacts. So these are areas that need to also be paid attention to as we move forward with decarbonization plans. With that in mind, again, tied to the large consumption of our cement-based materials, we also see large impacts in other categories. This is a quick summary of a handful of different air pollutant emissions down here at the bottom, as well as our greenhouse gas emissions. Oops, actually, this is supposed to say carbon dioxide emissions. I apologize for that. Energy demand and water consumption as a fraction of our global carbon dioxide emissions, energy demand, water consumption, and air pollutants, just from the cement sector. And as you can see, again, tied to that high level of consumption, cement is contributing relatively high burdens across the board. With that in mind, I will leave the presentation here so that we can move on to the next speaker, although I'm happy to discuss this with anybody and of course discuss it more on the panel. And of course, I want to thank the funders who have supported the research so far.
Thank you very much, Sabbie, for the very insightful sharing on the environmental and also from the consumption ends. Impact on their assessment methods to mitigate ecological burdens of material production. And so we really enjoyed your sharing, and I also personally very much look forward to dive into more the complexity of the infrastructure materials in the discussion session and about their life cycle analysis. So now let's thank Sabbie again, and we move to next panel presentation by Dr. Sergey Paltsev from MIT. So Sergey is a Deputy Director of the MIT Joint Program on the Science and Policy of Global Change. He is a Senior Researcher Scientist at MIT Energy Institute, and he's a Director of MIT Energy at Scale Center. So he is a lead modeler in the charge of their MIT economic projection and policy analysis model of the world economy. So his research covers a wide range of topics, including the energy economics. I'm pretty much sure he will share a lot about that, and the climate policy, taxation, and advanced energy technologies. Let's look forward to his presentation. So Sergey, your time.
Yeah, thank you very much. Thank you very much for the introduction. And thank you, Angela and Sabbie, for such a great overviews. I'll try to look at this decarbonization of the hard-to-abate sectors in a slightly different approach and slightly different dimension. So by my first degree, I'm an electrical engineer, but then I switched, what is called dark side in some corners, and that dark side is economic and finance. And so that combination actually helps me and helps our group to try to understand, well, with all these nice promises, what we have heard from Amory, Lovins, and other things, well, how much of that is actually reality? How much of that is profitable now, and what kind of technology and policy dimensions we need to look into the future to better understand where we're going. So again, I'm going to, I think we'll provide a little bit more realistic picture down to the reality, but at the end, since I'm from MIT, I'm also going to show you some of the things which might change the game quite dramatically, and I'm really hoping for that's going to happen. Obviously, during my time, I'm not going to be able to cover all the aspects. So, I'm going to put some of the papers which are related to hard-to-abate sectors, which we recently published. And again, I encourage you to go to our website, which is Global Change MIT EDU, and try to see what kind of analysis, what kind of studies we are doing in other sectors of the economy. And I will elaborate on that a little bit. But again, from these publications, you can see that we have a look at the analysis of hard-to-abate sectors in particular regions. We look at alternative fuels, we look at the advanced technologies, and currently, obviously, we are looking very, very closely at hydrogen and other pathways for other hard-to-decarbonize sectors. So here we are focusing on heavy industry, but other hard-to-decarbonize sectors also include aviation and shipping, and what are the options for decarbonizing those sectors is also extremely important for the success of reaching the Paris Agreement goals. This is a busy slide to show you what kind of tool we usually apply in order to understand, well, how big of the contribution for particular industry, or how big of the share of the emission reduction for certain activity. Because, well, one thing, the world is not homogeneous. So, and whatever the solution which may work in Colorado may not work in Shanghai, or whatever the solution which is going to work in Hamburg may not work in Lagos, Nigeria. And so you actually need to put that type of the granularity in terms of the local conditions in order to understand, well, what are the pathways for deploying particular technologies. And another point which I'll try to persuade you that it's not enough to look at a particular sector. So it's great to look and dive into iron and steel or cement or chemicals or other industries. But, well, after all, we live in in the economy which has a lot of interdependencies. And so we should take a look, well, if we put much more capital into something, well, it means that we are not going to have that capital for something else, for like health services, for education. And so if we are talking about mobilizing capital for clean energy, well, we need to make sure that we are counting everything which is related to the economic activities. And well, that is going to help us to ground to the reality a little bit more than, well, the statements, oh, well, we will be easily convert everything to low carbon energy, because it's not going to be easy. It's going to be very challenging, and it's going to require a lot of efforts. And another point is international trade is extremely important. And that's exactly what we are trying to capture with our tools, because it's extremely important, and especially now with change in geopolitics, how these international flows are going to change. So, for example, if we are talking about European border carbon adjustment mechanisms, so how that is going to change the profitability of different industries, how that is going to change the trade flows. And similarly, well, the recent changes in energy markets also might affect things in quite dramatic ways. So the point is, you need to consider that at economy-wide, global, multi-sector, multi-region fashion in order to understand the interlinkages between heavy industries, hard-to-abate industries, and the rest of the economy. Because after all, well, we are producing cement because, well, we want to have better roads, better buildings, and other things. And so we need to make sure that we are taking that into consideration. And I would even move forward that it's not only about the economy, it's also about the impacts. And this is where we need to connect our technology, bottom-up models, economy models with the impact models in terms of the water, in terms of the land requirements, in terms of the productivity of land, in terms of understanding how extreme events are going to affect different assets, both in terms of the energy, in terms of the agriculture, in terms of nature-based solutions. So again, this approach is going to make sure that, well, we are not overlooking some indirect impacts. And in many cases, well, those indirect impacts might be quite sizable. Now I'm going to switch a little bit more on, well, what are the current assessments in terms of, well, the economics of decarbonization. And again, after all, you are not going to employ, well, cement with carbon capture if there is no incentive. Because if you are going to take a look at this diagram, which one can find in the recent publication from International Energy Agency, and, well, many of other agencies, many of other institutions are trying to do similar type of the assessments. Well, what is the cost of doing business as usual versus what is the cost of decarbonization? And, well, again, so in this diagram, what we are seeing is just some limited options which are available. So we are comparing, for example, unabated cement with cement with carbon capture. But there are many other options for decarbonization of cement. And so you can do, as we have heard from the previous speaker, well, you can do alternative binders, you can do alternative fuels. So you can think of shifting to bio-based fuel, shifting from coal to gas, shifting to more use of waste materials, shifting to hydrogen. Or you can replace that clinker, which Sabine has so nicely described, well, with some alternatives. So, well, you can do, for example, fly ash from coal power production, or you can use slag from steel production. And again, well, then you're having linkages, and when this is where you're trying to understand kind of what is doable, what is possible in addition. But cement is very, very tough to address and very tough to go into really net zero profile. Because as Sabbie has mentioned, a lot of emissions are coming not from fuel use, but from the process. And so it's very hard to eliminate those emissions. So you can do fuel switching, you can decarbonize fuel, so you can do a lot of things in terms of the energy efficiency. Still, the process emissions are going to be sizable. And currently, it seems like, well, our best bet actually in carbon capture and storage, and I'll elaborate on that a little bit more. Similarly, for steel, there are many, many challenges. And so, yes, you can go to electric arc steel production. Well, you can, again, go to hydrogen. And there are a couple of the very novel projects right now in Sweden, where indeed we are thinking how to use hydrogen both as a reducing agent and also as a fuel. And again, you see that even in this somewhat optimistic picture, you see that, well, the cost of doing that is actually quite high. It's much higher than the cost of traditional steel making. And it means that, again, the economics has to be there, the policy has to be there. And same story about the chemicals. So Angela has mentioned that WRI is going to issue a report on decarbonizing chemicals. I'm really looking forward to that report, because it is extremely challenging even to understand, because it's so many chemicals, so many processes, and they are so heterogeneous and so different in different parts of the world, that there is no one unique answer, no one unique solution. At least in cement, you have one product, one homogeneous product. And so, well, yeah, there are some variations, but more or less you are producing the same thing. In terms of the steel, again, there are different categories of steel, but again, you are producing pretty much the same thing. In chemicals, that's not the story. And that, again, much harder to address. And again, well, there are some big chunk of the chemicals. And so what we are showing here, ammonia, methanol, and again, you can do some connection with fuels. So you can use, for example, producing green ammonia or green methanol, and then use that in order to help those sectors which I have mentioned, and use it for sustainable aviation fuels, for example, or use it for shipping. But again, it's a lot of challenges. But what I want you to take from this diagram, that the cost is going to be higher. So we shouldn't fool ourselves that it's going to be no cost or be already profitable. It is going to be higher. And well, I can share you at least one experience. A couple of weeks ago, I was at the conference in Spain, and I don't speak Spanish. And the taxi driver was talking to me all the way from airport to my hotel, and I understood it perfectly. He was talking about high gasoline prices in Spain. And so he was complaining because, well, the gasoline price is rising, and you see a lot of reaction, a lot of actually dissatisfaction about that. So if we are going to change the whole way how we are getting energy, how we are getting materials, we have to be really, really careful about the consumers, about how that is going to affect consumers, especially how that is going to affect low-income consumers. So what I would argue that we kind of know the technologies, we kind of know the economics. We don't really know how to put the policy which is going to be supported by the customers, where we are not hurting customers, but we are helping customers. And that is going to be quite challenging. And those who are trying to simplify that challenge, they're just fooling themselves. And unfortunately, that's not really the case. So, well, what we do at our program, we actually go one step further. So again, Sabbie have shown a different version of the diagram of cement production plant. And the story is, well, all these components in cement production, if we really want to capture something, the best bet in terms of the carbon capture is amine-based post-combustion capture. Well, if you want to do the post-combustion capture, well, you need steam. And there is no steam generation whenever you are producing cement. And so it means that, well, actually to do the carbon capture or CCS unit on cement plant, well, you also need to have some kind of boiler, coal-based or natural gas-based or whatever the fuel you're going to use in order to provide that. And that is going to add the energy penalty. But, well, that is also going to allow you to capture about 90 to 95% of your emissions from the energy and the process. And so that's why the CCS seems to be a better answer, better equipped, because you are actually solving both of these CO2 streams, and you're capturing out of the flue gas the whole thing. Again, well, you can do some innovative things about what you do with extra heat or extra electricity. You can sell that, you can integrate that. So there are certain things. And again, I provide you the link to the publication where we discuss that. And but it's not going to be cheap, and it's going to be quite challenging. And again, think about adding something like that somewhere in India or Africa or Indonesia. That will be quite challenging, but we are producing cement everywhere in the world. And so that will require quite substantial contribution. Well, we also can think of technologies where we don't really have the technology readiness level as post-combustion capture. So the post-combustion capture, which I have shown on the previous diagram, basically we already have that. We know how to do that. Again, it's extra cost, but at least technologically we know how to do that. So here is another example, and again, more references you can find on our webpage, which I provide down below. Something which is called cryogenic carbon capture. So this is another technology where you actually do not need to build that steam production facility because you're using electricity. And so you basically solidify your carbon dioxide from the stream of the cement plant, and you cool that CO2 to negative 140 degrees. And so then you are applying some hydrocarbons for separating that and putting that for pipeline to transfer again to either to store it or use it in other uses. So like sustainable aviation fuel, which I have mentioned, or other potential uses. So again, technologically, we know how to do that. This is a little bit lower technology readiness level. You are going to save a lot of capital because you don't need to build additional thing. But while the cost of electricity is going to be higher, overall cost probably is going to be lower. But again, that will require some innovative solutions how to go forward. We have done a study. So at the beginning, I have mentioned the study which we have done for India. So what is our thinking in terms of the economic impacts of decarbonization of hard-to-abate sectors in India? And so in these two diagrams, I'm showing you the emissions in the reference case. So we still have some policies, but the mild policies in the reference. And then you see what is the impact of the policies where we are imposing some kind of the emission restriction, in this case, carbon price, and with introduction of a CCS in India. You see that it's a very, very different picture, but it's still, we are not at zero. So again, whenever you are talking to zero and beyond zero or to negative, that's actually a very, very difficult thing to achieve. And so, again, I'm going to bring that to attention again and again, that it's not going to happen automatically, and it will require quite aggressive changes, both in terms of the technology, in terms of the policy, but also in terms of the customer acceptance. Again, I advise you to go and take a look at the publication where we discuss what kind of options we see in these particular sectors of Indian economy. And since I'm from MIT, usually the audience expect, how MIT is going to help. solve the world? Where is that magic solution where we can employ and basically we will enjoy our way of life and go into the future? And so kind of we can keep that for a Q&A session later on about kind of this alternative. So the figure on your top left, that's Spark. Well, that's our fusion plant. So that's a prototype which we are building now at MIT. And so again, we can discuss a little bit more. That's obviously very complicated machinery where you have hundreds of millions degrees of Celsius. And well, no material is going to hold that. So that's why we have a magnetic field which is going to hold that. And literally, we are building that right now, very well, like about 50 kilometers from our MIT campus. And kind of we already at least trying to see what is the design, how that is going to go. That futuristic picture on your top right, that's a nuclear battery. So that's another source of power. And so what is nuclear battery? Well, it's a relatively small device. So if we are talking about nuclear energy, well, the typical nuclear power reactor is about 1 gigawatt, so 1,000 megawatts. So this thing, nuclear battery, is about 10 megawatts. So much, much smaller device. But the point, you can fit it in a shipping container, and you can put it where you need the energy. So you can put it next to your steelmaking facility. You can put it next to your cement plant. You can put it somewhere in Africa where there's no access to energy. And the point that this is produced at the industrial facility, or at least that's the hope, that's the design. So kind of we are still working on that. But it's kind of in terms of the components, we again know how to do that. But again, another a great thing about that after you've done that, after 10, 15 years of using that, you just ship it back to the industrial facility. So no issues about the nuclear waste or something like that. So that's another technology which might change how we are thinking about the future, how we are changing about the energy needs. And coming back to cement, so that lower picture which you see down below, well, you actually can add carbon fibers or nanostructures. And well, you can do that to the product of the methane pyrolysis, where you're producing hydrogen. And so those carbon blocks can substitute and replace the construction materials. So again, very early stages, but we see some good promises. And even more than that, if you do it right, those nanocarbon blocks, you actually can use cement, your buildings, as an energy storage. So think of your building as a big battery. And so, well, that's a solution for the energy storage. So again, some excitement about what the future can bring. But you remember all those cautions which I have provided you at the beginning. Well, that will take time. That will take a lot of efforts. And if I would predict how the future is going to look like in terms of the industry, I hope it's going to look something like that. But I don't know when that is going to happen. And I don't know what would be the cost of going there. But let's hope that we will arrive at that future rather soon. So thank you very much.
Thank you very much, Sergey, for the nice sharing, shed light on the dark side of the economics, financial issues according to this like green transition of the hard to abate section. So, and it's very unique view to connect all the possible solutions to reality. I mean, I agree with you, like make whatever solution you are going to apply, make that profitable is a final like incentives to all. So we need to work more on that side. And thank you very much for highlighting the issues with cement and some innovative possible trials with like carbon fibers. We can discuss later, like with Sabbie in the next session. Now let's welcome Mr. Zhiyuan Fan from Colombia, who is going to sharing his view on the iron and the steel making. And Zhiyuan is currently working at the Center on Global Energy Policy. He supports his carbon management research initiative, focusing on low carbon industry systems, including low carbon fuels and processes, CCS, and CO2 use recycling. So let's welcome Zhiyuan. Zhiyuan, showtime.
Yep. Thank you so much for your invitation. Let me try to share my screen. Yep. Yeah, thank you for the invitation again. Today I'm gonna share a little bit view about low carbon steel production, what are the options we have today and the assessment about these options. I'm from Columbia University, as introduced, the Center on Global Energy Policy. So if you have any questions, feel free to reach me or reach the center. Decarbonization of iron steel industry is very, very important because it contributes to 6% of global CO2 equivalent emission. That is a bigger section than all the cars combined. So if you believe that decarbonization through electric vehicles will be a very impact solution, you have to focus on materials such as iron steel and cement. In 2018, over 1.8 gigaton of steel hot metal is produced globally, and to produce that, on average, 1.85 ton of CO2 will be emitted per ton of steel hot metal production, and a $400 cost will be paid. That will add up to over 3 gigaton of CO2 equivalent per year, and that is the data for 2018. And the most recent data shows that China is producing over half of global iron steel, and China's production exceeded 1 gigaton alone in 2021. And that is how much we produce iron steel globally these days. And we will come into a little bit more details about how we produce iron steel. The overwhelming majority comes from the technology called blast furnace, basic oxygen furnace, BF-BOF, and that is a process design that's been last for centuries. 71% from blast furnace-based production, and the rest goes to EAF, called electric arc furnace-based steel production. It can use different kinds of feedstock of iron. Mostly will be scrap metal stocks. That means EAF scrap metal will be the recycled steel production. And the rest go to roughly 5% will be a little bit more innovative and less carbon intensive way called DRI, direct reduced iron, that allows more energy efficiency, hydrogen capability, and less emissions. About the options about how to decarbonize this giant industry, there aren't a lot. We only have a handful of options today, and we basically already covered all of them in the previous discussion by other panelists. The first one will be hydrogen. You can inject hydrogen into blast furnace, but they only give you like 20% decarbonization potential. Overwhelming majority will still left, but low carbon hydrogen injection will have a much bigger role to play if it's DRI, direct reduction iron. We can use biomass. Biomass will play a very important role, roughly 10 to 15% across the whole society, and will also play a very unique role for iron steel because it can replace some of the coal and coke using biocoke or biochar. But it also has some leftover CO2 emission, and the biomass resources itself suffers from some other limitations or CO2 emissions from life cycle analysis or land use change. We can always do electrification. Is probably the most intuitive ones because we know how to decarbonize the grid better than we understand how to decarbonize the heavy industries and hard to abate sectors. But decarbonization with electricity need electrification first, but there's very little room for blast furnace, but better chances with DRI and EAF. And finally, we have talked about this many times, carbon capture and storage is always available for heavy industries. It is possibly the most cheapest option among all of them. With all of these assumptions, we can also explore the combination of them, maybe all of them or some of them, that will give us a better chance to reach net zero as soon as possible. Here we compiled all of these options applied on different technologies to produce iron steel, and their decarbonization potential is what we focus on first. Because the target is net zero, we have to reach 100% decarbonization potential in order to reach net zero. However, it is very, very hard for iron steel industry, especially for blast furnace-based production. Blast furnace-based production has a very high carbon intensity, but also very, very stubborn to any decarbonization approaches. They're all highlighted in yellow. Most of them are on the upper half, meaning they have less than 50% decarbonization potential with these different approaches. So we will have a better chance to reach deep decarbonization and eventually net zero with EAF-based solutions using scrap metal to produce recycled iron steel or using DRI, which has a less CO2 intensity. Another concern will be absolutely the cost, and it's actually the main challenge for any of the decarbonization approaches. Lots of these approaches will have a production cost increase higher than 25%, and CCS is possibly the cheapest option comparing with hydrogen, biomass, or electrification. I also want to shed light on a very important topic. It's about the policy implications. Policy is possibly the biggest driving character that could drive some difference in the near-term or long-term future. We have discussed a little bit about the national policy and international policy from the results we have derived before. The high abatement cost really limits a lot of conventional policy values that we typically discuss. For all these approaches, we will need a lot of infrastructure. We will need power grids, we'll need CO2 pipelines, we'll need hydrogen facilities in order to get to decarbonized iron steel industry. But unfortunately, these infrastructure does not exist today. And also, this high abatement cost makes iron steel industry and generally the heavy industry very insensitive to carbon pricing policy. The typical carbon price policy will range from $20 per ton of CO2 to maybe $100, but it's still not enough to cover the cost increase for most of the options except for CCS. And in order to protect the local production with decarbonized technologies, we also need to probably apply some border tariff, but that also means the border tariff has to be really, really high. And as we discussed, blast furnace produce most of the iron steel today, but it's very stubborn to decarbonization. So we must consider an asset replacement strategy, replace blast furnace with other production pathways. And those replacement has to consider the local optimum. Do you have the resources by your door, such as hydrogen or biomass or CO2 storage capacity? And also we need a lot of policy to support the deployment and also to drive the cost competitiveness issue for the increase of the cost. We can consider a replacement grant to replace blast furnace, government procurement, just to make sure that the green steel get purchased first, and we have to provide special incentives to the early adopters. Otherwise, without the policy support, the green steel will just be a more expensive product that is not, whose carbon credit is not fully considered. Internationally, the handful of countries will produce overwhelming majority of iron steel and most of the industrial products as well. China, Germany, India, United States, Japan combined will cover likely 70% of global iron steel production. So we need an international standards to coordinate the decarbonization for these main countries. And it's very important for us to bring companies into this discussion, especially the state-owned enterprises, the SOEs in China. We'll find the best model to engage this cooperation. Border tariff can be applied, but it's not likely to deliver any abatement other than collect some money. We can consider the Club of Nations. Quite a few, just a number of nations combined will produce a lot of impact about the influence, how to set up the standards, and we can have a parallel effort happen with the G20 or Paris agreements, but none of this is happening today, so we have to drive them as soon as possible. And of course, we will need an innovation agenda. As I mentioned, there are not a lot of options available today, so if we really want to try more, we need more options in our pockets. And that basically concludes my presentation. Thank you so much. I welcome any discussion in the coming session. Thank you so much.
Thank you very much, Zhiyuan, for the very nice sharing and highlights the potential opportunities there. Including collaborating with the companies, get them involved and to see what's the possible solutions there. So thank you very much for the sharing, for other panelists in this session. Now we are moving to discussion part. So we got half an hour to go. So I want to start with a broad question. So what are the key challenges where the hard to abate sections are facing, like cement and concrete, iron and steel making are facing towards a net zero? So let's first discuss about the key challenges. Angela, do you want to start?
Well, I'll probably end up just echoing Sergey. I think the high cost is what seems to be getting in the way of even getting started. And so there are things that governments can do to try to reduce those costs, and there's some of that beginning, but I think there's that, and then there's just a general resistance to change that is often a factor in any industrial process, and the complexity of once you change one thing, what else has to be changed? So those would be the two overarching things I can come up with.
Yeah, so Sergey, do you want to add some comments here?
Oh, I think well, we're in the full agreement with Angela. Yeah, so yeah, we just need to find what are the innovative ways, what are the solutions, how the government can help, right? Because one way or another, we need some government support in order to do that. And so again, in different locations, while there are different instruments, so like in the United States, well, we usually like to give subsidies. We usually like to give money, right? And so the recent Infrastructure Act, which Angela has mentioned. So yeah, there is a sizable amount of money which is available there. So like for carbon capture, it's about $10 billion, which is available. For hydrogen, it's about $8 billion available for some pilot projects for hubs. And so, well, again, that's hopefully is going to bring those high costs. And so that hopefully is going to help how to move that. But also on the consumption side, again, we just need to make sure that there is a customer acceptance, so that there is pressure from shareholders, there is a kind of demand for that. So Zhiyuan mentioned the green steel. Well, if there is no acceptance, if there is no willingness, if like, well, for example, car makers may say, okay, well, we will accept only green products if we are going to produce cars. So, well, then that is going to jumpstart. But again, one way or another, we would need to think what would be the right way how to support different industries. And as I have mentioned, in cement, it's even more difficult. And well, Sabbie, it looks like she knows that area better, so I'll switch to her if she wants to add anything.
Yeah, Sabbie, your call.
I mean, I'll echo the others. I really do think that that's going to be what some of the main drivers are going to be tied to the economics. I mean, the additional complexity ends up, in my opinion, also being linked a little bit to some supply chain aspects. So who's responsible for which components of the material, as well as the materials use, as well as the materials disposal, and are they getting incentivized to make changes? But of course, that just highlights the exact same points, and it's hard to get that to happen. Yeah.
Yeah, to follow up the question, so I'm also wondering from techno-economic aspects, so what are the common challenges that we could leverage to optimize the decarbonization efforts? So who wants to start? Maybe Sabbie?
Yeah, I can start, and then
Okay,
let's see if we're in agreement. So again, this idea in the US, at least, that gets more and more prominence of looking at hubs, right? So not just deploying that like uniformly, but okay, well, let's try to find a location where we have conglomeration of industries. So for example, Houston, right? So this is where we can produce hydrogen, and this is where we can get the uses. So there is a very good infrastructure. There is acceptance, at least for carbon capture, not as in comparison to many other locations. So I think that's the way to go, where you're integrating. Because again, if we are talking about hydrogen, well, it's only part of the challenge to produce hydrogen, and that's already expensive, especially if you're talking about green hydrogen. Well, another challenge is how to store that and transport, and that will add substantial to the cost. And so if you do these hubs, if you do these solutions, integrative solutions, this is actually where I agree with Amory. Usually I don't agree with him in many cases, but that's one place where I agree with statement that these integrative solutions are extremely important, and we should be looking for that, and that is going to reduce the cost, and that's going to hopefully jumpstart at some pilot locations, which then we can also expand in other areas.
Yeah, thank you very much, Sergey, for the role of hydrogen play in the process. So actually yesterday in panel 3, we had a lot of discussion around that. If anyone is interested, you can refer to yesterday's panel discussion around hydrogen. I have one question, follow up this. So Zhiyuan has mentioned something about like hydrogen play in the iron making process and how to make that process cleaner. And Zhiyuan, do you have further sharing the progress? I mean, you have published one article with Joule, which give a very comprehensive discussion on where the hydrogen comes from and how can that serve the iron making process to make it the decarbonization more efficiently. And do you want to share further the progress there?
Yeah, absolutely. Thank you so much. As we found for a lot of research, hydrogen is always the Swiss knife to cut through the difficulties about decarbonization, especially for heavy industries. It is uniquely true for iron and steel because hydrogen can provide the two most important things that make iron steel. The first one is provide the high temperature heat that is definitely required. The second one is provide the reduction agent. So hydrogen provides the chance to fully decarbonize the iron and steel industry. For cement, it's going to be a little bit harder because the process emission will still remain. This is the unique thing about iron and steel industry, that hydrogen will play a more important role. It is also shown in Angela's slides as well. So hydrogen have a higher electrification potential and even higher electrification potential if we consider hydrogen as electrification process. And for iron and steel industry, the most important challenge is that we need a lot of hydrogen. So the scale of the hydrogen supply must be secured, and that will be a consistent supply. So I will say that probably blue hydrogen will play a more important role for industrial facilities due to the scale, due to the load factor, duty cycles, and etc. So just one more follow-up about Sergey's thinkings about, for example, automobile industries could purchase a green steel. That exactly what's happening. Recently, we heard the news that BMW is the first buyer about the world's first batch of production about green iron steel using green hydrogen in Germany. So I think that is a pretty good start that the company got involved into this process. We're seeing something being developed soon and hope the scaling up of this process could happen in a faster speed.
Thank you very much. Very nice sharing and inspiring news from the BMW. And so I'm also curious, in other talks, we mentioned a lot about CCS. I'm curious about their part CCUS, what's the role it can play, and what's the current status of coupling CCUS to their hard to abate sectors. Do you have any thoughts? Who want to start first? Angela, do you have any comments here?
Yeah, I'll just say that obviously CCS is I think more in use in the United States than other countries. It's primarily in use by the power sector right now, and over time we think that that's actually not the best use of CCS. That there are it would be better used in the industrial sector. So there is a lot of optimism within the industrial community about adoption of CCS. And the infrastructure law just passed also provided not only the money to install essentially, but also to do the front end engineering studies to get these companies ready for CCS. So, you know, the real test is going to be the next few years, and which countries, which companies and industries really decide to invest in it and make it happen. The other thing that is I think a key to the success of carbon dioxide storage is moving away from utilization through enhanced oil recovery and into geologic storage. Some part of it, there's some really interesting utilization innovation going on in terms of new products and services. There's some discussion of using captured carbon for jet fuel. I think there's a company that in our initiative that is doing that, but that's probably not. There's not nearly as much capacity to store the carbon in those products as underground, and just creating that system of underground storage, the monitoring requirements, et cetera, and gaining community acceptance is going to be a big challenge too.
Yeah, fully agree. And now I want to take advantage of my chair role here to ask one difficult question here. So the circular approach, as we know, is a core of driving a net zero transition of the hard to abate sectors at system level. And so where and what are the circular opportunities we could harness them? So Sabbie, do you want to start?
I'm actually not entirely sure I understood the question. So are you asking about how this can contribute to the circular economy?
Yes.
Okay, so in that case, I mean, there's a handful of examples that have come up. Unfortunately, cement and concrete, it's actually one of the more difficult materials to reutilize in that fashion, because once the cement is hydrated, it's really hard to undo that particular switch. There's been a fair amount of work in the architectural realm of, well, if we've built a component, how do we reuse that component, assuming that it hasn't undergone some form of failure? There's, as I mentioned with the presentation, maybe we could use our crushed concrete to at least recarbonate and then use it as a road base or some form of downcycling. But what's actually some pretty cool research out of some of the cement plants in Europe also is looking at what happens if we take cement that has already hydrated and use it as the raw material feed to produce more cement. And since it has already off-gassed that limestone decarbonization gassing, we actually potentially have a raw material that can facilitate more cement production without the limestone decarbonization. It's in the research phase, but there have been a lot of discussions of how do we start to reuse this material, even though this particular classification of materials is one of the more difficult ones too. Did that answer your question? I'm worried I went off on a tangent.
Yeah, this is very innovative source. I think the idea here is quite exciting. So it's still on the research stage, right? And I want to hear what Zhiyuan think about for the circular approaches in iron steel making. Will that contribute to that sector overall?
Yes, today the recycled steel already contributes roughly a quarter of the total steel production. And certainly it can play an even bigger role. For example, 1/3 or even half, that is totally doable, but we need a lot of things to do before that. We need to collect the reuse. We need to collect them first and then figure out the most efficient way to reproduce them. And that will be the most important thing. And actually, that is the easiest way and the cheapest way to decarbonize the iron steel industry. And I think that could be the similar structure for other heavy industries as well. And in terms of that is recycling of the materials, there's also a chance we can recycle the captured CO2. And the biggest chance for reusing the CO2 is actually through producing low carbon fuels. the carbon-containing fuels such as methanols or other long-chain hydrocarbons will also give a probably hundreds of million tons or gigaton level potential of CO2 reusing. That is because we are still going to use a lot of fossil or carbon-based fuel in the future, for example, for aviation, for shipping industry, and for some hardware-based sectors that is particularly stubborn to other technologies. So I think those are the two chances that we can focus on in the future.
Yeah, it's good to see we're doing innovative trials about the circular approach. And I want to hear Sergey's opinion, how that can be connected to the reality. Do you think it's profitable?
Yeah, no, I think that's extremely important. And that's extremely important in hard to decarbonize sectors. And I think Sabbie and Zhiyuan already provided very good answers to cement and iron and steel. I want to broaden that. So it's not only about the industries, it's other materials, right? So like batteries, if we are talking about electric cars, well, it's a lot of materials which need to be recycled because the mining is going to be challenging, right? So if you are going to take a look at the typical electric car, and you will see that typical electric car requires 6 times more minerals in comparison to conventional car. If you are going to take a look at, for example, wind turbine or solar, the story is similar. You need much more minerals if you are trying to go to low carbon economy. We are talking a lot about hydrogen. Well, if we are talking about the PEM electrolyzers, proton exchange membrane electrolyzers, well, there is a key catalyst in there, and that's iridium. And that's an expensive material, and 80 to 85% of that is in South Africa. So it's a lot of geopolitical implication as well, unless we do recycling. And so that recycling is going to be important both for the products, well, for the critical minerals, also, well, like whatever we use, like plastics, other things, all that is extremely important. And indeed, again, we need to find a way how to incentivize that, because, well, if it's cheap to throw away, well, you keep throwing that away. So we need to find a way, okay, how to provide an incentive to do that recycling. So I fully agree with the previous speakers on that. Sure, we need to do more.
Yeah, that's very insightful view. And now I want to ask the one last question for this session. So what do you think is the future priorities like for decarbonizing heavy industry? So Angela, do you want to start there to be the first?
I don't think I have a great answer to that. We're kind of in this state, right, where we talk a lot about low-hanging fruit, and it's still not easy to get to that low-hanging fruit, I guess. I think it's going to be some first movers. I think some of the companies that kind of make the investments, get out front will, and they're able to demonstrate that they can do it profitably. I think that's going to help stimulate systems change in the industry. So, and I also think some of these global discussions about tariffs and border adjustments and standard setting, I think all of that may begin to create some just reality signals to the companies that this is going to happen, right? And they can, they can get on board. They can be an early first mover and get some of those benefits, or they can wait and hope the costs go down and it's cheaper for them to do it later, right? So there's a lot of dynamics at play.
Mm-hmm. Yeah, I fully agree with you. Like the standard setting is a very important part, and every company, every country is setting their goals, but how to evaluate whether they have meet their targets. So yeah, I really look forward to all the progress on a standard setting part. And so Sabbie, what's your view on like their future priorities for like cement materials development?
My view on the priorities are let's do everything at once now, hurry. So I realize that that's not actually giving you a legitimate priorities list, but in reality, I think that there's many solutions that could be implemented. They're not all going to get us to net zero, but any type of movement should be done where it can be. And the nice thing is, because there's so many different solutions, we could actually start to implement ones that make the most sense for a regional or local basis. So maybe there isn't a one size fits all for the entire planet, but for individual regions, this type of solution where we use the material more efficiently is going to be best. In this other area, maybe we could switch fuels more easily, and that's going to be best. And yes, ideally, eventually we will do it all everywhere, but we just need to start making movement quickly. So that's my 2 cents.
Yeah, pretty solid. And Sergey, so what's your view?
Well, you have such an easy question, right? So, well, I kind of in between Angela's answer and Sabbie answers. Yes, we need to do all of the above. So, unfortunately, the urgency of situation is upon us. And well, even though I have provided a lot of realism and other not so rosy picture and what is ahead of us, but at the same time, well, we know that we have to decarbonize as fast as possible. And kind of that's what scientists are telling us. That's what we see actually, kind of we experience that firsthand, that we have these more extreme events which are going to be upon us. And so my hope that, well, the customers are going to demand much more. So I think this is where we need to educate actually the public as well as much as possible. So that's exactly what you are doing with your journal, with this conference. And in general, we need to reach not just to practitioners or researchers, but the general public, for them to understand, well, what it would take, that they should be asking, well, their the representatives, the companies, that they need to act. And so hopefully that is going to create a momentum. And we see a lot of that in Europe, actually. So in Europe, it's much more aggressive and much more we see in terms of the support to decarbonization. And this is where you see a lot of impact on financial companies. And so the financial companies are demanding, well, show us that you're actually reducing emissions, otherwise we are not going to provide you capital. And so kind of that type of the pressures from different sides, from customers, from policymakers, from investment communities, hopefully that is going to start moving us much faster to where we need to be. And so, yeah. As Angela, I don't have a good answer. Otherwise, it's not going to be hard to decarbonize, right? So we have a title, Hard to Decarbonize Sector. And there is a reason for that, why it's hard to decarbonize.
Yeah, I fully agree. At least now we know the incentives, so we should move towards that. So Zhiyuan, do you have anything to add on in iron making, industry? What's the future priorities for your field?
Yes, from Center on Global Energy Policy, so I will bring 2 more points on the already established talk. So from policy point of view, so can you hear me?
Yes, loud and clear.
So the most important thing about the policy will be, the first, it has to be a standard about the CO2 emissions. If we care about the decarbonization, we care about CO2 reduction, all these standards has to be carbon-based. So it has to link to CO2 emission in order to drive any real changes in terms of decarbonization. That is the very first thing. The second thing is, I totally agree with Angela's point that even the low-hanging fruit today is not low enough for us to reach it. So we have to build the steps, build the stairs for that. And the most important one will be the very foundation of any changes will be the infrastructure. So the plans, the facility really cares whether we have the hydrogen at my doorstep. Do we have biomass resources near me? Do I have pipelines that I can pump my CO2 that is captured in my facility into that? So the infrastructure will be the most important foundation in terms of the reality to drive any changes.
Yeah, I agree. Having their standard first, then set clear step-by-step goals will help us to achieve their final goal. I fully agree that. And before we close this session, we still have time to invite every speaker here to give you a chance to summarize what your view here and what you want to say to your peers, to their policymakers, to the stakeholders, like what do you think they should do to contribute here? So may I start with Angela for your summary?
Sure. I think there's a lot of seeds being planted right now throughout the industrial sector, in academia, in the halls of lawmakers, state legislators, congresses around the world, and it's all important and doable. So those early investments are gonna be really important, and if the industry kind of has some strong alliances, right, and they all kind of jump off this cliff together, I think we are gonna see real progress, and we can accelerate the progress that we're seeing right now.
Yeah. So, Sabbie, do you want to add some summary here?
Oh, I agree fully with that. I really think, so, I mean, as a background in engineering and in materials development, I realized I should say, let's just develop new materials and give up on these ones. But in reality, we're pretty locked into the materials that we have. And I think that policy could be one of the largest drivers in getting this to break, and incentivizing the right organizations to make this sort of change. So I agree with what the others have said so far. Yeah.
Yeah. So, Zhiyuan, do you want to give a brief summary and call for attention? What kind of efforts you want people to input into your field? So, Zhiyuan, can you hear us?
I'm sorry, I'm having some connection issues. Sorry. Can anyone pick up the steps? I have some hard time hearing anybody else.
Yeah. Hello, Zhiyuan. Are you still with us? Okay, maybe we go with Sergey first for the summary.
Well, kind of in terms of the summary, well, we already discussed so many dimensions, and so it's not just one-dimensional solution. So there are a lot of things which we need to take into consideration. I think I would like to to do, well, somewhat a summary or somewhat a final statement about the word of encouragement, to those who are currently trying to look at this issue, trying to develop new materials, trying to develop new approaches, that we need all of that. So we need all of the wisdom, we need what you do, and we need more. And so no matter how small your contribution you think, it's still important, because we need to put all the emissions to zero. So it means that even the small scale applications, small scale solutions are important. And even more in terms of encouragement, I hope that policymakers have the courage to do these things, which are not that popular, and it's hard to persuade the public to do them. And again, the policymakers has a limited amount of time, and while the benefits are going to be much further away from their political window, and that's a tough decision. And so again, I would love to encourage that we need to do these actions, and we need the leadership in order to make sure that we are decarbonizing as fast as possible.
Yeah, thank you very much for call for all dimensions of contribution at all scales. I'm sure with that, we will move towards faster to the net zero targets. So now we're almost timing here. Thank you very much for joining this board and sharing your insights. I really enjoyed your views, your analysis. I'm sure the audience also take home a lot message here. And so I also want to call for attention for our next session, because it's hard to abate. It's a big topic, very hard topic. for the decarbonization. So we will discuss transforming trade and freight. So we will come back to this room again 30 minutes later. So let's join me to thank our speakers again here and enjoy some good rest. I know it's very late now for you, Angela, Sergey, and Zhiyuan. And also thank Sabbie for keeping here for so long. I don't want to keep you too long before your dinner. Okay. So thanks again. And we look forward to more discussions in the future. Thank you very much. Take care. Bye-bye.
Thank you.
Bye-bye.